Welcome to this lecture. Before proceeding forward, let us first quickly recall what we have been doing in this week. So in the first lecture, we have defined the integration of measurable functions with respect to a given measure on the domain side. And in the second lecture, we have started discussing about properties of this integration procedure. In particular, we have discussed two special properties. One was multiplication by constants or scalars, and then another property was a comparison type inequality. Okay, so now in all of these, our idea is to get some nice properties of this integration procedure which will make our job in computing these integrations easier. Okay, so this is what we are targeting. So in particular, one of the major properties that is still not proved is the linearity of the integration. By that I mean, if you have two functions, let's say g and h, then addition of g and h, if you consider the integral of that should be computable as integration of g plus integration of h. So this is something we are yet to prove. Okay, so before proving that, we cannot in fact use this property in our arguments. So we'll have to be careful with this. So anyways, so let's start off with the discussion in this lecture. So we move on to looking at certain very special type of integration procedure. Okay, so in the previous lecture, we have continued the discussions about integration of h with respect to the measure mu when h is a measurable function, right? And mu is a measure on this domain side. All right. So with that at hand, let's first focus our attention to this kind of a set function. So we had defined this in the first lecture of this week, that once you are considering a function h, then look at the integration of h over the set A. And how did we define it? We considered h times indicator A, which is also a measurable function. So therefore you can consider the integration of h times indicator A. Whatever that integration value is, consider it to be the integration of the function h over the set A. And now, given this measurable function and given this measure, fix them, then try to vary these sets capital A from the domain side. Once you keep varying this set capital A, you are going to get different values for this integration, provided these integrations exist. If you now vary these sets, you are going to get all these values, and then what you end up having is a set function. For each set, you get some extended real number if the integration exists, and hence you can look at this set function for each set A, alright, in the domain side. Then what we do is that we are going to look at the properties of this specific type of an integration in this lecture. So before proceeding forward, we need to understand what kind of structures does this function have. H times indicator A. Okay, so let's see. So if you take two sets from your domain side, look at the product of their indicators. It's an easy observation that you can actually write it as the indicator function of the intersection of two sets. Okay, and using this observation, you can now make this nice observation that start with a simple function which is a linear combination of indicators. Then you multiply the simple function by this sum indicator. You can rewrite this in terms of again certain indicators. So what is happening here is that you have this product of indicators coming up here, and then this product of indicators by the observation above can be written as the indicator of the intersection of the sets. So therefore the simple function multiplied by an indicator still remains a simple function. We are going to make use of this observation in our next result. In this lecture, we have assumed that h is a measurable function and mu is a measure. Now assume that h is also non-negative. So now here h is non-negative and measurable. Then consider the integration of h over the set A. As per definition, it is the integration of h times indicator A. So therefore, as per definition, what you need to consider to compute this integral is to look at all simple functions below h times indicator A. But we are saying there is another way of doing this. So that's what this right hand side suggests. So what is in the right hand side? Forget about h times indicator A. Look at all simple functions small s below the function h, and look at the simple functions integrations over the set A. So that's all you need to check. So you don't have to go to simple functions below h times indicator a, but look at all simple functions below h. Consider their integrations over the set A. If you can manage to compute all these quantities, consider the supremum. That supremum will agree with the left hand side. So that is the statement here. So how do you prove this? So you have assumed that h is a non-negative measurable function. Now if you take a simple function that is below this function h, then observe that by multiplying this inequality on each term by indicator a, you end up with this relation, that s times indicator a is still a non-negative simple function and s times indicator a is less equal to h times indicator a. Great. So you have that is following from the previous observation. But then you have these inequalities, and we had proved these inequalities for the corresponding integrations in the previous lecture. So following that result, you can now look at the integration of s over the set A. That is nothing but the integration of the function s times indicator a. Now s times indicator a is smaller than s times indicator a, and therefore integration of s d mu over the set A is less or equal to integration of h over the set A. So that's all it requires to prove this inequality. Now take supremums over all such simple functions below h. So that is what is appearing on a left hand side. Okay, so therefore supremum of all such simple functions that are below h, if you consider the integrations of that over the set A and consider the supremum, that will be upper bounded by integration of h over the set A. But we want to show the equality here, right? So we want to somehow get the other sided inequality. Now what do? You will now start with a simple function that is below h times indicator a. So our target is to compare with the integration of this function, correct? So therefore you start with a simple function which is now below h times indicator a. Now observe that on the complement of the set A, this relation will tell you that s is 0. Why? Because if you take any point small omega on the complement of the set A, h times indicator a is 0. So therefore s on those points on the complement of a is also 0. So therefore you can identify s as s times indicator a itself, right? So this is a nice observation. Therefore in this case, when s is a simple function below h times indicator a, therefore integration of s will be the same as integration of s times indicator a. But that is nothing but, in our notation, integration of the function s over the set A. Great. Now consider the integration of h over the set A. That is nothing but the integration of h times indicator of a, right? So this function. But this function integration, follow the definition, you have to consider all simple functions that are below h times indicator a. Consider their integrations and consider their supremum. So that's what this definition suggests. But then you have just said that for such simple functions, integrations of s is nothing but integrations of s over the set A. So I have just made use of this equality that s is 0 on the complement of a. So it will not contribute there, right? So that's all we are using here. But then these are for any simple function that is below h times indicator a. But any simple function that is below h times indicator a is also below the function h. Okay, and therefore this is a bigger class now. Okay, so any simple function that is below h times indicator a is also below the function h, because h is non-negative. So therefore you are considering a larger set of functions here and considering their integrations, and these are all non-negative quantities. So therefore what you get is a supremum over a smaller set is less equal to the supremum over the larger set. So that's all you are using to write down this inequality. Okay, so therefore what happens at the end is this last inequality is giving us the other side of the inequality that we wanted. So we had earlier proved that h, integration of h over the set A is greater or equals to this supremum. Now we are saying integration of h over the set A is less equal to this supremum, and therefore once you have these both sided inequalities, you get the required equality. So this is very easy to prove. You just have to keep track of which measurable functions you are working with, and you have to appropriately choose the corresponding simple functions. Okay, so once you go through this argument, you have managed to show that integration of h over the set A can be computed very easily as integrations of all simple functions below H itself, and you just have to consider the integrations of these simple functions over the set A. Great. But with that at hand, we can now make very nice statements. What is this? So start with the fact that integration of H exists. So assume this. So once you assume that the integration of H exists, then you can immediately claim that integration of H over the set A also exists. So why is this? Here we are going to make use of comparison type inequalities. So here start with the positive part of H times indicator A. So here note, we have not assumed H to be non-negative. So H could be taking any real values. So here H times indicator A, the positive part of that is nothing but the H plus multiplied by indicator A. Indicator A is always taking non-negative values. So therefore that's what happens. But then you immediately observe that H plus times indicator A is smaller than H plus. Similarly, look at the negative part of H times indicator A. So that you first write it as H minus multiplied by indicator A. But this product function is less equal to H minus. So once you have these two inequalities and provided integration of H d mu exists, you can now claim that one of the integration of H plus and H minus must be finite. So if both are finite, then H is integrable. If exactly one of them is finite, the other is infinite, then H is quasi-integrable. In either case, at least one of them is finite, and hence, without loss of generality, let's assume first that H plus has a finite integral. Then what you will claim is that integration of the positive part of H times indicator A, that will also have a finite integral. Why? Because H times indicator A, the positive part of that is dominated from above by H plus, and H plus, if it has finite integral, then H times indicator A, positive part of that will have a finite integral. Therefore, you have managed to show that if you look at the measurable functions H times indicator A, then at least one of the positive part or the negative part will have a finite integral, and hence integration of H in times indicator A will exist, and that will suggest that integration of H over the set A exists. This is simply rewriting the condition in terms of the comparison type inequalities. Great. Now you can make a stronger statement in the case when H is integrable. So if H is integrable, then let's go back to these integrations once more and consider the inequalities. So here you assume that both H plus and H minus have finite integral. Here what is happening is that the positive part of H times indicator A will have the integration to be finite because it is dominated from above by the integration of H plus, which is finite. Similarly, the negative part of H times indicator A will have its integration finite because it is less or equals to integration of H minus, which is given to be finite. And hence, since the function H times indicator A has this interesting property that both its positive part and negative part has finite integration, then H times indicator A becomes integrable. So that proves it. Great. But then you now make this observation. This is a very minor observation but quite useful, that if H is integrable, then integration of H is a real number, right? Because it is the difference of two real numbers, meaning it is the difference of integration of H plus and integration of H minus, both being finite in the case when H is integrable. Now, using these integrability structures, you can now look at integration of H times indicator A. So the positive part of that will be having finite value once H is integrable. Similarly, the negative part of H times indicator A will have a finite integral when H is integrable. So provided this happens, then integration of H d mu over the set A, that quantity will also be a real number. So this is a very interesting fact. When H is integrable, then not only the integration of H is a real number, integration of H over any set is also a real number. Of course, the set has to be chosen from the domain side sigma fit. Now, we now restrict our attention to non-negative measurable functions. So again, throughout we are assuming H to be measurable. In addition, if H is non-negative, we might get some very nice interesting additional properties. So what happens here? So take h to be non-negative measurable. Then we know that integration of h d mu exists. You don't have to consider the integration of h minus, you just have to consider integration of h plus. So here integration of h d mu exists, so this could be taking infinite values, of course. Okay, so this takes values between 0 and infinity included. Here we also have the inequalities that h times indicator a, so that is nothing but the integration of h over the set a. So this quantity h times indicator a is dominated by h because you are talking about a non-negative function h here, and indicator is simply a non-negative measurable function. So using this comparison type inequalities, you will claim that the integration of h d mu over the set a has this kind of structure. Okay, you have this upper bound given by integration of h. Great. Now this is what we had started off this lecture, that we are going to fix h, we are going to fix the measure, we are going to vary the set capital A, and in the case when h is non-negative, the integration of h over the set A is also some non-negative quantity, and it will give you a nice non-negative set function. How nice? That is stated in this proposition. So take h to be non-negative and measurable, consider this set function nu, which takes any set to the integration of h over the set A, and you are going to claim that this is a measure. So if you integrate a non-negative measurable function and integrate over this sets A and vary the set A, then you get a set function that turns out to be a very nice set function which is non-negative and countably relative, that is a measure. Okay, so we are going to prove this fact. Alright, so we start with the case when h is simple. So again h is given to be non-negative, so you have to work with a non-negative simple function. So here look at this combination xi indicator bi. Okay, so xi are certain non-negative real numbers because h is non-negative. Great. Now what is happening here is that what is the integration now? Integration of h over the set A is h times indicator A, and that is, as per our observation, is nothing but this linear combination of xi multiplied by this indicator of the intersections, right? So that's something we had already mentioned right at the beginning. Great. But now as per definition, this integration is nothing but summation of xi multiplied by measures of A intersection bi. So that is by definition. Great. So again here all the terms xi's and measures are non-negative, so defining summation is not an issue. Infinity minus infinity situation does not arise. We are only dealing with non-negative quantities. It could be infinity, that is fine. Great. So this is our definition. So integration of h gives me this set function, and the set function here takes this explicit value. We are going to use this to prove that for the case when h is simple, this set function is a measure. So what is going to be proved is the countable additivity. So start with a pairwise disjoint sequence of sets in the domain side sigma field. Then observe that if AMs are pairwise disjoint, then if you fix any I, then AM intersection BI, these sets are also pairwise disjoint. This is for any fixed I. Then use the fact that this set function nu has this form, that it's this linear combination of the measures of this type of intersections. Now use the fact that mu is given to be a measure and use the countable additivity over the sets AM intersection BI. So you will get this additional summation over M coming out. This is by countable additivity of the set function of the measure mu. Now exchange this order of the summations. So the summation over M goes outside. Here it is allowed because you are dealing with non-negative quantities. Now here inside you have this finite sum over these quantities, and here what will happen is that these bi's, as per construction, these bi's appeared due to the decomposition of the simple function, right? So let's go back to the description. So if you take h to be a simple function, we automatically assume that these bi's are pairwise disjoint. So just use the fact that measure of that set function nu has this form to write this inside combination as nu of AM. Great. So you have managed to show that when h is a non-negative simple function, then this set function is countably additive and therefore it is a measure. Okay, great. Now how do you go from non-negative simple functions to non-negative measurable functions? So this requires some effort. So again, start with a sequence of pairwise disjoint sets, call them AM once more. Our target is to prove that the corresponding set function is countably additive. So you have to be careful with certain inequalities here. Here the main issue is that integration of h, which is non-negative and measurable, is defined through certain supremums over integrations of simple functions below h. So start with such a simple function which is below h and s is non-negative. Then look at this multiplication by indicator. So s times indicator of the union of the sets AM can be written as this summation of the functions. Why? This is easy to verify. Put sample point small omega on both sides and verify this equality. So what is happening here is that indicator of this union of this pairwise disjoint sets AM can be simply written as the summation of the individual indicators. So that's all we are using here. Great. Now for every fixed M, if you look at the inequality that S is below H, then by multiplying by indicator AM, you still have this inequality here. So you have S times indicator AM is less equals to H times indicator AM. So this is true for any fixed M. And hence if you do the integration of this for every fixed M, integration of S times indicator AM is less equals to integration of H indicator AM. So this is simply following that comparison type inequality that we discussed in the previous lecture. But then you vary your M. What you do? You look at this summation of the first such k many terms. So if you look at that summation, then here what is happening is that this is the summation of M from 1 to k of integration of H over the sets AM. That's what these integrations are. But as per definition, that is the set function nu of AM. That is by definition. This is the summation here. But then this nu of AM, by definition these are non-negative quantities. So in particular you can dominate it by the full series. So this full series need not converge. This full series can be plus infinity also. It doesn't matter. The inequality still holds. So this finite sum is of course dominated from above by this infinite sum. So because these terms nu of AM are non-negative. Therefore for any fixed k, integer k, you have this summation from m equal to 1 to k, integration over all this simple function is dominated from above by this quantity which is now independent of k. So the right hand side, this final quantity that we ended up with is independent of k. Therefore you use the fact that the set function A mapping to integrations of non-negative simple functions is a measure to go from k to infinity, and you will use this bound here. So that's all we are going to use. So first use the fact that A mapping to this integration of this non-negative simple function S is a measure, which we have already proved. We have that we can push this integration inside, right? So for simple functions this is already a measure, so therefore you have this finite additivity, so therefore you have this union happening here. Okay, so that's all you are using, because this set function becomes a measure for non-negative simple functions. So this is just rewriting the equality for finite additivity of this measure in question. Great. So therefore what you have now just proved is that integration of S times indicator of these sets is dominated from above by some quantity which is independent of k. Again, this quantity that is happening on the right hand side, this is a positive real number or plus infinity. Now again use the fact that for non-negative simple functions this set function is a measure to go from this limit, this is basically limit of finite additivity going to countable additivity. So take limit as k goes to infinity of this finite sum. Now this finite sum, as already observed, is nothing but this, but then using the countable additivity you get this limiting value, this implies continuity from below. So therefore this, since these sets increase to the whole union, you will get this limit will give you this integration. Okay, so here you are using the fact that this set function is a measure, and in particular it's continuous from below. So since this finite union increases to the whole union, that's what you will get as the limit of these integrals. So that is nothing but this integral value of S over the union of these sets AM. Okay, so here you have used multiple times the fact that for non-negative simple functions this is a measure. Then what you have managed to prove at the end is that S times indicator of all these unions is dominated from above by this summation. Okay, great. Here the new function is defined in terms of the general function h, which is non-negative and measurable, and S is a non-negative simple function which is below the function h. So this is true for any such simple function. So you have this upper bound appearing here. So if you take supremum over all such simple functions, you get nu of am on the left hand side and summation of the individual nu of ams on the right hand side. So you have some kind of a countable subadditivities for the set function nu. You want to prove the other side of the inequality. Okay, and that will give you the appropriate equality that we are after. It will imply that nu will be countably additive. So how do you show this? To show this, again start off with this observation that for every fixed k from 1 to 3 onwards, h times indicator ak is dominated from above by h times indicator of the whole union. And therefore if you consider the integrations of these functions now, that is nothing but that nu of ak is dominated from above by nu of this union, right? So that's all. So since these functions have this relation, their corresponding integrations also have this relation, and therefore nu of ak is dominated from above by this quantity. Great. But if it happens that nu of ak is infinite, then of course that nu of this countable union will also have infinite mass. Therefore you will get the countable additivity in this case when nu of ak is infinite for some k. But now let's consider the finiteness condition, that nu of ak is finite for all k. So this is the interesting condition, and here we have to separately prove the countable additivity of the set function nu. Here what is happening, if you fix any k and fix epsilon positive, you can now find a simple function small s below h such that the integration of h d mu over the set am is approximated by these simple functions. So you can choose such a simple function with this error epsilon by k. So you can choose this. This is given as an exercise. The hint is that the supremum over all such simple functions that you consider is exactly going to give you the integration of h over the sets am, right? So that's all we are using here, but we are saying you can choose a common simple function s here. So try to work this out. This is left as an exercise for you. But then what is happening here is that look at this inequalities. You have already observed that for this countable union, whatever this set is, this contains this finite union, and therefore you get this inequality. So that is already proved. But now this finite union is nothing but the integration of h over this finite union of sets. On this finite union of sets, use the lower bound given by the simple function small s. So since s is below h, you have this inequality. So that is simple to observe. But then here this sets am are pairwise disjoint, and integration of s d mu over such sets is going to give you a measure. So you use finite additivity to write it as a summation of the integrations of s over the sets am, and then you use the inequality that is left as an exercise here to claim that this is also further greater or equal to the integration of h over the sets am minus epsilon. Put them together. Once you get this, you will get that rewriting it in terms of nu, it is nothing but nu of am. So that is nothing but the definition of nu of am being used here. So what did we start off with? We started off with the nu of the complete countable union, and that is greater or equals to this thing minus epsilon. But since this is true for every fixed k and every fixed epsilon positive, you get that this inequality is true. This is true for any k now, and hence if you let k go to infinity on the right hand side, the left hand side is independent of k, and therefore this will give you a upper bound, and that is the upper bound we were after. We had proved the other side of the inequality, and hence the set function nu is countably additive, okay, and therefore it becomes a measure. This series is upper bound for nu of this countable union. Great. Okay, so we have this result, and using this observation we now make some interesting comments that if h is non-negative and integrable, then nu of omega, whatever that is the integration of h over the whole set omega, that is finite provided h is integrable. So therefore you get a finite measure provided h is integrable. Otherwise, if it is just non-negative and measurable, then the integration of h will give you a measure. In particular, you can now have these observations about continuity from below that will imply these limiting behaviors for the corresponding integrals, that if am's increase to the set A, then integrations of h will over the sets am will increase to the integration of h over the set A. So this is for non-negative measurable h. This is simply using continuity from below of the set function nu. And we end with a short discussion on other interesting properties of this set function. So you can try to show that if mu is sigma finite, then the measure that we have constructed out of integrating this function h will also be sigma finite. Please try to check this. Here we have discussed the results for non-negative measurable functions taking values in the real line, but you can actually do all these arguments for extended real valued functions but non-negative functions. So you allow plus infinity for possible values of h. So again the similar results can be discussed in an analogous fashion. We will continue the discussion of properties of integrations in the next lecture. We stop here.